proof, another proof was the one of the very first one we started with was proving that square root of 2 is irrational.
Right.
So remember that one. So the proofs are such as that are certainly fair game. So there won't be a lot of proofs. I think the whole test contains maybe 2 at most. If
This
you
one or our test, you mean?
oh that test, yes.
This one only has 1.
It's got the last one. It says, except for the last problem, all explanations are optional. The last
Right.
one.
So there's only 1. Well, there might be 2. Like I said, so one of the definitely will be induction, and the other might something else. So that would be example of proving that square root of 2 is irrational. Would be one, well, a type of a proof other than induction that might be on the test. Okay, so well, you know, the proof wasn't easy, so that I'm not positive actually. The proof is a little bit long actually in comparison to some others that we have seen, especially at the very end when we talked about one-to-one onto. The proofs are like two lines usually. Once you figure out what's going on with those, possibly with those arrows, then the proofs are shorter. This is not as short if you remember how we did it. So the starting point is that you should be familiar with. The idea of the proof is this: P over Q. The definition, then take a square, 2 is equal to P squared over Q squared, and then you have Q squared 2 is equal to P squared, and then using the fundamental theorem of arithmetic, factorization, prime factorization of these two numbers, will demonstrate that this is impossible. So but it is a multi-step proof. Okay, the proofs that we have seen more recently are not as long. In fact, but they are abstract. So, well, this is still induction, so let's skip that. But the proofs that we have seen, like these, for example, that bijections form, they create an equivalence relation on sets. Okay, so there are little proofs there, but the challenge, it appears to be, for the most part, is making the right reference. So for those 3 axioms. The existence of inverses, the uniqueness of the inverse, the fact that the existence of inverse implies that the function is one-to-one onto. All of these do not take a lot of writing, as you can see here, but they are quite abstract in comparison to those to what we started with early on. So that's a separate challenge, and there will be some set theory and functions in this test. Anybody that has looked at the final from last year? So, well,
I'm scared.
I'm just taking it one at a time.
well, what I meant is you just get more ideas of what might happen, even though the final is closed book as opposed to open book. But there are still problems that are actually more relevant. Say set theory might, I can't remember, but well. A couple of times. Okay, so if we scroll all the way down, the final exam from 2 years ago. Okay, so so some of the problems are similar, as you can see. This is very similar to what we just talked about. Contrapositive, converse, negation, induction. Examples, and this one is that is not on the sample test, but we did talk about that. So that could be a problem for you to consider because that would be appropriate for the upcoming test. As you can see, give example whenever possible of the following functions: 1 onto and 1 1-to-1. Okay, so I didn't mention what Z2 is, but it's just 0 and 1, two numbers. List all bijections of the set 1, 2, 3 to itself. Okay, prove the composition of two onto functions is onto. So that does not directly apply because it is a problem that we have had. So that is why the problem is appropriate for a closed book test. So that's why it's here. Group. Okay, we haven't talked about that. Composition. Look at this problem. Compositions. So, do you know how to form compositions from tables?
Have we basically covered everything that's on the final?
You just
No, no, the groups, no, certainly not groups.
Oh, yeah, just groups.
Yeah.
Groups.
Metric, triangle inequality, so it's a metric once again, so there's some stuff. But this one isn't. So what is h of 0?
So what is
H of 0, yes.
1.
H of 0, it is, yes, it is 1. How do you know? Well, I mean, the assumption here is that it is f followed by g, even though it's not explained. But so f followed by g. So how did you get from 0 to 1?
y equals 1 when x equals 0?
That's right. So you go from x equal 0 to y equal 1 in the first table. Then you find that 1 in the first row of the second table, and then go down once again to z, and so, or u rather, and that's how you get 1. Okay, so if you start with, say, 4, so if x is equal to 4, then y is equal to 2, find 2, and the answer is 2. Okay, so, well.
So if it were h of 3, it would be 1.
H of 3, no, it is, 3 goes to 0,
Oh, yeah, right.
and then 0 goes to 3.
Okay, yeah.
Okay, so, well, so that tests your understanding of things that may have appeared more in algebraic form than a tabular form, but it is certainly a very crucial skill. Okay, so take another look at it. So as an extra test, you should know whatever has or has not happened in class in order to discard some of the problems that we have discussed. Okay, so so numbers still might appear. So set theory has so many possible problems, but number theory as well. Remember that another problem that was not on the list, anything about congruences. So not just as a particular example of equivalence relations, congruences. We started with those proofs. Remember, even plus even is even, things like that. So that's the congruency analysis pretty much, and so it might also come up. And the last topic was not this, not that. Okay. The last topic was products and graphs. Okay, so remember these teeth. That's the end of the topic for the test. Okay, so products and not graphs, not so much. We just to remind you that what we are after is the place for the graph of a function to live in. Okay, and that's why we build products as simply pairs of elements of x and y, and so that's something we care about. However, there is another issue here that I would like to look into. And that is, what if we go backwards? Suppose we have a product. As you can see, what is the graph? The graph is a subset. So that's the crucial part. Where does the graph live? And it lives as a subset of x cross y. Okay, so if you understand cross y, then you put then the graph, that's where it will end up. But what if I pick any subset of a product? What's going to happen? So well, to remind you, so subsets of x cross y. As an example, I take x squared plus y squared is equal to 1. It is a subset of the plane, of the xy plane. So in other words, it is a subset. So the equation is not a subset. It is the set is, say, r is equal to xy's. with x squared plus y squared is equal to 1. Okay, it is a subset of the plane which happens to be r cross r. These are x's, these are y's. Okay, so that's you remember this is a circle naturally of radius 1, centered at 0. Okay, any recollection of what we call this? X squared plus y squared is equal to 1. Or you can tell me what this is not. It is a subset of the plane, but what it is not the graph of a function. Remember this? Does it sound familiar? The circle is not the graph of a function. Why not? From pre-calculus?
Some x values that were below y.
That's right. So also known as the vertical line test, and indeed it has. We have two values for each x. So the input is right here, x, and then it will produce two y's. Okay. So so it's not the graph of a function, which is what we really want to talk about, but there is a word for it. It is the graph of what? There is a separate word for it, a relation. Does it sound familiar? Functions versus relations. So it is a relation that you relate x's to y's. Okay, so you can relate them by function, but there is something more general that relates numbers or elements of sets. It is called a relation. Okay. And so in other words, what does it mean for this particular example? It is if x and y lie on that circle, they are related. Okay, so say 1, 0 related, 0, 1 related, 1, 1 not related. Okay, so you check every point on the xy plane can be checked against this relation. You check, do they satisfy the equation? If they do, they are related. Okay, if they do not, they are not related. Graphically speaking, every point on the graph is xy is then represents a pair of related quantities, x and y. And then every point of the circle represent a pair that are not related. And then what that comes up in pre-calculus, and then what you do is frequently is that you can extract a function from a relation. Remember, extract one or more what's the function or functions? Circle. What do we do with the circle? Does this look familiar? What?
Y equals x squared and x squared plus 1.
1 minus x squared.
Yeah.
And this one, the other one is for the bottom, y equal negative 1 minus x squared. Okay, so these are functions. These are functions, and these are their graphs. Okay, so then our relation is actually made of two functions, and its graph, that circle is made of the graphs of these two functions. Okay, so frequently you could have, so this one is the relation that is not a function, and only a function is under certain circumstances you can extract some information, and that's just as an example. I don't want to do more examples than that, but that's how it works out. If you cut it in half, then each half satisfies the vertical line test, It is the graph of a function. So we identify those functions, and then we know so much, but probably not, doesn't come up a lot. But the relation is really hard to study because they try to plot a relation in comparison to a function. It's very easy to plot a function x, compute, get y. Take x, compute y. You have a bunch of points. You plot it. The end. That's how all the plotting is done. On the other hand, if you speak of relations, then all you have to do is like this: pick a point and verify, does it satisfy the relation or not? Then you plot it. If it does not, you don't. So you have to go through the whole plane, every single point, in order to figure out what the graph is. So that, even though this is a very convenient representation of a circle, and that's quite popular, it is very hard to use it to plot. You see it, right? So it is clearly what it's supposed to say, that distance to the origin from point x, y is 1. Okay, but it is, and so that's the definition of a circle of radius 1. But it is sort of mentally in your head, but really if you want to practically see something more complex than just a circle with similar relation, then you probably will have a hard time plotting it. So that's why we study functions, and that's why this transition is important. And but the definition is quite interesting. Any subset of x across y is called a relation from x to y. So a relation, any subset in the product. So for example, any subset of the plane will give you some kind of relation. So circle is just one relation, but you can think, how about, well, you take a square, you take like this. This is still, all of these subsets are relations. So if the point x, y belongs to this set, then they are related. Okay. That's a very simple definition. We probably should then say specifically what makes a relation a function. So that's the crucial one. So what is so special about the graph that we would know as a subset of xy that would make it, which would guarantee that it is a graph of a function? Well, the answer is naturally the vertical line test. Okay, so well, that's pretty much. I don't want to put it in the form of a theorem, but a subset of x cross y is, well, subset say G is the graph of a function. And at this point, well, if and only if, what is the restriction that we have, that we all know what it is? It is illustrated graphically with the vertical line test. We just need to put the vertical line test in the form of a statement, set theoretical statement. So, what makes a subset the graph? These are x's, these are y's, and we have a subset. So we know that this is not a graph, but this is. So what's the difference? How do we put it in the form that is independent of referring to xy plane or vertical drawing lines? How do we say?
Each input only has one output.
Well, there is no input-output, but let me put it this way. There is at most one y for each x. So for each x, there is at most one y. Well, naturally, what we're talking about is xy that belongs to G. That is simply vertical line test, except there is nothing vertical there because it's all set theoretic. But you can see how that works out. So once again, for each x, there is only one y. That way, if there's only at most one y, then you can say that you can define function at least for those values of x for which there's at least one y that defines a function. So define f of x is equal to y. So there is at most, and we know that there would be no more than one. Okay, so we know that for that x, that function will be defined, but it is possible that there is none, there is no y, then the domain will have to be shrunk from x to something smaller. So let's look at once again a subset G of x cross y is the graph of, but not any function. How about a function that is one-to-one? What makes it one-to-one function?
Same thing for every x is the most one.
No, you got to reverse it. Remember? You got to reverse x and 1.
Oh, okay, for every.
Right? That's one-to-one. Right? For every y, there is at most one x.
How do we know when we have to switch it up like that, though?
Well, the function, and then the function goes from x to y. It matters which way it goes, from x to y. So once you have a function, you can sort of make it better behaved, so that you can reverse the arrows. And I don't think I mentioned this, and that this is really a big deal. This is all business about one-to-one and not. It's about solving equations. So on a very fundamental level, so nothing but solving equations. And then we're just talking about, so y is equal to f of x. That's your equation. You're trying to find x for y. So y is given, find x. Okay, that's what the solving an equation means, right? So, and then if the function is one-to-one, what can we say about the solutions? If the function is one-to-one, there is only one x for each y, at most, right? Which means that there could be at most one solution. When the function is onto, it says that there is a solution. And when it's one-to-one and onto, there is a solution and there is only one solution. Okay, so in linear algebra that especially comes up a lot, and it is very important to classify linear functions in that manner. So it's pretty much there aren't too many choices for what can happen. You can have one solution, linear equations, one solution, no solution, or infinitely many solutions. So it fits very well with the it's kind of a set theoretic analysis of the function you're looking at, and so you have to know what kind of function it is. So graph is not just a graph of any function, but a graph of a function that is one-to-one. If for each y there is at most one x with x, y, and g. Okay, so it is. Another word for it is the horizontal line test. So you can have the same picture, but now you try to go this way, and you can see not only the first one violates the horizontal line test, the second one also violates the horizontal line test. For it to be one-to-one, it has to look like this. I mean, like it might not be covering the whole thing, so it's not onto necessarily, but it has to have one intersection with the horizontal line. So that you may have seen in pre-calculus, right? And then you can have a similar theorem for the onto. So onto, and we already know what the answer is. For each y, there is at least one x with x, y, and g. So that does not correspond to the x, y, to any kind of horizontal or vertical line test. So what relation would be onto? Well, it depends depends what your x and y is. So say let's say this is x, and let's say this is x, and say this is y. Okay, so what visual properties of the graph would give you a function that is onto? So, well, let me put an end to it like this. So, suppose this is my y, it's just an interval. The graph would have, well, is this onto? It's not onto because there are values that are not covered. So this y does not have a counterpart. Okay, so you still go with the horizontal.
It also has to be continuous.
No, it's not. It doesn't have to be continuous. No, what it's about. It's more like about the projection of which is the image, as a matter of fact, or the projection of that set on y should give you the whole y. And so that is an example of how some values are missing. And how do you see it missing? If it is on the plane, you draw a horizontal line, and it has to hit the graph. If it does not hit the graph, then what? It means that the function is not onto. It means that the equation has no solution, and that's how we know. Okay, so there's a bunch of problems that appear here as well. So well, the proof is just as a homework. Just think about the last theorem. Make sure that the relation is clear of those definitions that we have to be talking about, one-to-one, onto, and at the same time this kind of point of view when things are happening not x and y separately, but rather they are just exist live in the x cross y, that kind of a new set. Okay, so it's not. It just takes some getting used to. Not really that hard. Once you get to the idea of what the cross product is. I'm sorry, not the Cartesian product. Okay, so the really big topic that we are progressing towards is infinity. But not the same infinity as in calculus. So not the calculus infinity.
Like a different kind of infinity?
No, it's totally different.
It's completely different?
Yes.
Wow.
Well, let's figure out what infinity means in calculus, just quickly.
I just assume infinity means you go on forever.
Well, it's not
Like
precise
never ending.
enough. In what context does infinity appear in calculus?
In sets, I don't know.
No, not sets, no. What?
Limits. Yeah,
Limits.
you're right.
Limits. The answer is limits. So every time you see infinity, the only way to think about it is there is a limit behind it.
But the term infinity stays the same. It's just being used in a different context. Is that what you're trying
No,
to say?
we'll see in a minute, but let me just remind you. So limit, say, n
As it goes to infinity.
is infinity. Well, let me, maybe I don't want to use LIM, but n goes to infinity, n squared goes to infinity. So that's what it means.
Yeah.
Limit. So the definition of limit will then follow. I'm not going to, as promised, I'm not going to do calculus. But if you want to really understand the infinity in calculus, then that's what you would have to do. You have to look up the limit, infinite limit, not just any limit, an infinite limit. Okay, either sequences or functions, doesn't matter. So x squared goes to infinity as well, as x goes to infinity. So you have to look up the definition of limits, and you see what it is. It is a sequence of what, by the way? These are all numbers. So we're not doing numbers anymore. So we're doing set theory, and so the growth of numbers doesn't really tell us what we care about. We care about sizes of sets, in that sense.
Is the second infinity, like as x goes to infinity, because x is just a big set, right?
No, there are no sets here. This one? No, these are not sets. These are numbers. These are all numbers.
I'm saying the x, like you said, so or as x goes to infinity, is that infinity not the calculus definition?
No, they're all numbers.
So what's
This is all calculus.
So what's this new definition?
It's not a new definition. It is what we care about. We don't care about how large numbers are, how they progress through by means of some function or sequence. We care about sizes of sets.
So it's infinity in a different context. Like
In a very different, yeah. Well, even though you probably can connect them if you really care, but certainly there should be no confusion between the two. A size of the set, period. A size of the set. We know that the size of how many integers there are, the answer is infinite. So in that sense. So the symbol is the same symbol, but that's all the relation so far. So I don't know if from the top of my head I cannot connect them very quickly. These one infinity with the other infinity. So like I said, we're talking about sizes of sets. Where in calculus there we would be talking about sizes of sets. Well, of course, every sequence is assumed to be infinite, and without that you cannot go to infinity. But that's the we're talking about magnitudes. So the magnitudes of numbers that grow without limit. That's the meaning of infinity in calculus. And we're talking about sets that could be infinite, and then could be more infinite. Some could be more infinite than others. But first of all, where does the similarity visible is that we do start with the finite sets. So finite sets are, say, 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, and so on. And we know how many elements. So if this is x, the magnitude of x will be 1, 2, 3, and 4.
So the above is basically saying the amount of numbers or sets that you can have is infinite. Like that's basically, like the possibilities are infinite is basically what that's saying. The possibilities of numbers.
Yes, it is, but then that we really don't want to stop there.
Right.
So that list is infinite, and from the point of view of calculus, that would be your infinity. We now in a way we imagine that we have made all of these infinitely many steps, and then we look where we are, and we have an infinite set, right? So the next one here is z, which contains all the previous elements, and then the answer is infinity, and that we what we want to understand. You remember that these sets are, even though I put it as an x, but really what we're talking about is not only specifically these sets, but also all x with bijections to one of these. So we are speaking there not of these sets specifically, but all sets, possibly all imaginable sets, because every set every finite set will have a bijection without one of those kind of sample sets. Okay, and but those aren't really that interesting because they're finite. It's where things starts to become complicated is when we deal with infinite sets. I guess we'll just look at it after the test. Okay, so see you Monday.